Radhe Radhe everyone. Today's Leetcode problem of the day is 3479, and I was initially confused looking at today's problem of the day and the yesterday's. Then I went ahead and compared the description. It was exactly same word by word. Only place where it differs is in the number of in the constraint, the number of elements in the fruit array and the basket array. Yesterday yesterday this constraint was 100. So our code was this for 100. Like for each of the fruit, we were parsing through complete basket array to find which is the appropriate basket, the leftmost one which is available for us to keep it there. And that we were doing. So for each basket, we were traveling through for each fruit, we were traversing through each of the basket. So this was big O of n square solution. So constraint was 100. So 100 square is 10 to power 4, which was feasible yesterday. But if we write the same solution today and try to run it, so today it's 10 to power 5. So if you square this, it becomes 10 to power 10. And if it is more than 10 to power 8, so it won't execute in Leetcode. So that's not an efficient solution. So we'll have to come up with a better solution. So what we can do is, rather than parsing through each element in the basket, what we can do is we can divide complete basket array into some chunk, and we can just see whether which is the leftmost chunk where we can insert the fruit, and we don't need to traverse each element. So for that we can divide it into chunk. Now how to divide this chunk? Should it be n by 2? Because see, I mean, it is not sorted, and we cannot sort it as well because we need to take the leftmost basket whichever is available. So if we sort, the order gets misarranged, and then we won't find the correct solution. So now the question is, we should divide this chunk in which manner? Should it be n by 2, n by 3, n by 4, or something else? So see, currently our solution is for each basket we are passing through each of the basket. For each fruit we are passing through each of the basket, so it becomes n square. Now even if we divide the basket into n by 2, let's say, so first thing what we'll do is we'll try to see if left side is eligible or not, or if right side is eligible or not. First thing is we'll check the left hand side because we have to fill it from left to right. So if we see the first side, and let's say we found out, okay, here we need to insert. So first time you did two comparison, like left or right, right? So n by 2 is the one which has the basket 2, which can accommodate the fruit. Now again, then in n by 2 you will traverse. So approximately 2 into first time twice you did whether left or right, and then for that n by 2 traversal you was required to be done, and this is for each fruit. So again it turns out to be n into 2 into n by 2, right? So approximately it turns out to be n square again. Now if we do n by 3, similar thing will be there. If we do n by 4, same thing would be there. So next thing is to decrement the power of 2, right? It is becoming n square. So what we can do is we can now deal in terms of power to reduce it. So how about square root of it? Okay. So if we convert into square root of it, so there are square root of chunks, square root of n chunks are there. So for each fruit, you will try to find which chunk is the suitable one from the left hand side. So it will be root of n, and then again in that root of n, you will try to find out which is the correct basket. Inside that, root and elements are there, but but it is not like for each of the root and chunks you are going through each of the element. You are finding out one chunk, and inside that you are going for root and element. So that is root n plus root n. So it turns out to be it is n into root n overall. So n raised to power n into n 1 by 2. So it turns out to be n raised to power 3 by 2. Okay. And in our case, n is 10 to power 5. So 10 to power 5 into 3 by 2, which is 15 by 2, which is 7.5 something, 10 raised to power 7.5 something. So it is less than 10 to power 8. So that solution will work, although it will take a lot of time. So that is one of the solution. But the question should be, I'll come to the board and explain this time complexity, whatever I have said. The question comes is, so we have removed the thinking of like n by 2, n by 3, n by 4. Now, why only square root we are taking? Why not cube root? Why not 1 by 4th root, 1 by 5th root? Why only square root? So, in brief, I'll tell you the square root is the optimum one, but why it is optimum, I'll tell you at the end of this video when I have solved this question, showed you time complexity, calculation of time complexity, then it will make more sense to you. Okay, so let me share my screen with the tab. So example is like this is fruit and basket given to you. So how we were solving was we were seeing 4 and starting to parse this basket array from left to right. So can we put it in this basket? No, we cannot. Can we put it in this basket? Yes, we can. So this gets occupied now. Okay, and this gets filled in. Now again we'll start with this 2. Okay, can we accommodate this in 2? Yes, we can. So this is filled up and this is covered. Now we'll start with this. This is already filled, this is already filled, this is there, but the capacity is less, so we cannot. So this we cannot. So in answer, we will return this as 1. Okay. This was the ask. Now, what we'll do is divide the basket into chunks and see from left to right if there is any chunk whose max value is greater than or equal to current fruits quantity. Okay. So for this, we will be doing square root decomposition. Okay. Now, so let's say if 9 elements are there, so square root of 9 turns out to be 3. So there will be chunk of size 3, 1, 2 and 3. So we will have a max array of length 3, which will have this. But there is one more place where people get confused a bit is, let's say what if an extra element is there? How will you accommodate that? If we have length 3, then we will miss out on that element, which shouldn't be the case. So for that, what we do is, whatever is our block size here, which is 3, okay, so on that, on this 3, if we add, block size is 3 for us here, so if we add here block size minus 1, so if this length is completely divisible by chunk size, this block size minus 1 will not impact anything, right? But if any extra element is there, it will make one more block, maybe one extra element or 2 extra element or 3 extra element, block size minus 1 extra element. Yeah, so what we do is we do length minus 1, length by chunk size, and in the length we add this chunk size minus 1 to accommodate if there is any extra element, if this length is not completely divisible by 3. For example, let's say if it was 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10 was there. Okay. So in initial case, our block size was 3. So if we did 9 plus 3 minus 1 by 3, which is 9 plus 12, 11 by 3, which is 3. So it didn't impact. If the length was divisible by 3, that addition of 2 didn't impact anything. Now, if let's say one extra element was there, then 10 plus 3 minus 1 by 3, 13 minus 1, 12 by 3. This will give you an additional chunk, right? Similarly, if you have 11 after this, so it will be 11 plus 3 minus 1 by 3, which is again 13 by 3, which turns out to be 4. Now again, let's say if 12 was there, one more element was there. Let me remove this. Let's say 12 was there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So again, this is completely divisible by 3. 1 chunk, 2 chunk, 3 chunk, 4 chunk. So 12 plus 3 minus 1 by 3 if I do. 15 minus 1, 14 by 3. This gives 4. So if it is completely divisible, then in that case, if you add this block size minus 1, this won't impact anything. But if there is any extra element from the block, then this will add an additional block. And mathematically also we can show it. Is what we are doing is we are doing total length plus block size minus 1 divided by block size. So if the length is completely divisible by block size, it will be something like x into block size then, and we do block size minus 1. This block size gets cancelled, this get cancelled, and this is, so on integer this will turns out to be 0 in integer, right? So this becomes x. Now if this is not divisible by block size, then what will happen is this will turn out to be, length will turn out to be something like this. Some part is divisible by completely a block size, and there is something extra here, and this extra can always be between 1, 2, 3 to block size minus 1, because if it's block size, then it will change this part, multiplication of this, it will become y or z or something, right? So this value can range from 1 to block size minus 1, and then we are adding one more block size minus 1, right? So if only 1 is there, so this 1 and 1 will get cancelled, right? And block size will be cancelled, so this will become 1, right? So this will become 1. So this will become x, for this 1 it will become x plus 1, right? This solves. Now, and at max what it can be is block size minus 1. So block size minus 1 plus block size minus 1, so it becomes twice of block size minus 1, right? So twice of block size minus 1, what it means is it is more than block size, but it is less than twice of block size, right? And when you divide this with block size, so it becomes 1 point something, and 1 point something, it turns out to be an integer is 1. So again it becomes 1. So this maximum value will be x plus 1, and minimum value will be x. So whenever it is divisible by block size, it will be x, and it will not, it becomes x plus 1. So people get confused on this one, that's why I covered this, just to I mean, this is our conclusion. What will be our max value array size? The number of chunks, okay? So whatever is your chunk size, you add minus 1 on the length to accommodate any extra element if you have, which if the length is not completely divisible by chunk. Okay. Okay, so this is covered. Now let's say we have this example. Okay. So basket length is 5 here. So square root of 5 is 2 point something. So approximately in integer we are taking it as 2. Okay. So if you are taking it as 2, number of chunk is 1, 2, and 3. One element is missing because an extra element was there. So yeah, so for each of them we calculated a max here for each chunk. So whenever we parse through fruit, we'll see from left to right in the max array, like if there is a chunk on the left side, or traveling from left to right side, if there is any chunk which can be used to accommodate that fruit. Okay. So for example, we started off with 3. We saw this chunk. Okay. This chunk has max value which is greater than number of fruits. So, and this corresponds to this chunk. This index is 0. It's correspond to 0th chunk. So what we will do is, and for each fruit when we start, we make unset as 0. If you're not able to find any, then we'll add this in unset. Okay. And if we have found it, then we'll make unset as 0. So for this fruit, we found it out, right? So we made it unset as 0. So in answer, nothing will be added. But now we need to figure out which basket exactly we will be using. We will make that basket as 0, and if it was the basket with maximum value in that chunk, then that maximum will be modified. We need to take care of that, right? So we came to this chunk. From left side we started parsing where we can accommodate it. We found like, okay, this is where we can accommodate this basket. So we make this basket as 0 so that it cannot be used further. Okay, and see, 6 was maximum in this chunk, which is now 0. So we need to update this. So in this chunk, though we have found the basket where we need to insert, we still need to parse this complete chunk to get the maximum value and update our this. So we went through this chunk and we found, okay, 4 is there, which is maximum. So we will come here and update 4. Okay. Now let us move to second element, 6. Can we accommodate it here? No. Can we accommodate it here? Yes. So again unset become 0 for this particular fruit. Okay, answer remains 0. So we found out, okay, this is the chunk. Let us go to this chunk. This is 1th index. So how will you find the position, like from where to where you need to do is the indices 1 into the chunk size, which is square root of 2. So in our case it is 2. So 2 into 1 is 2. So start from here. Okay, start from here, and number of element will be square root of 5, which is 2. So 2 elements you need to look for in this particular chunk, and this chunk starts from your this indices into square root of 5, which is your chunk size. Okay, so you started looking from here. This is, you looked at the first basket here and you found out, okay, 7 is greater than 6, we can use this basket. So make it as 0 and then parse through this, because as we saw in this, like the max got modified. So you see, like if its max is modified, uh, then you need to populate new max here, right? So you parse through this. Okay, so you found 8 is the maximum still. So 6 is also accommodated. Now let's start with 1. When we start with 1, unset is 1. We go from left to right. We see, okay, 4 is there, it is greater than this. Awesome. So let's go to this chunk. So index is 0, 0 into 2 to get the chunk starting index in the original basket array. 0 into 2 is 0. 0 is the starting of this chunk. So start from 0 for 2 elements and see whether if the basket has capacity to hold this. First basket is having 0, you cannot use it. Second basket is having 4, you can use it. So awesome, you found it. So make it as 0. Make it as 0. Make this unset as 0 so that you have found it and you don't need to add this in answer. And then you modify your max here, and this time the max becomes 0. Okay, now next fruit is 8. Okay, so you make unset as 1. You see first has got 0, you cannot use this chunk. The second one is 8, you can definitely use this. So you find out the starting of the chunk. So 0 into 1, 0 into 2, sorry, index is 1, right? 1 into 2, which is 2. So starting index is 2 in the original basket array. Give me a second, I'm having a call. So we see 1 into 2 starting from here, we'll go till we'll see 2 elements, and we found out, okay, first is not possible, second is possible, so we make it as 0 and modify this max value, which again becomes 0. And since we have found elements, so we make it unset as 0, so answer is still 0. Let's move on to the variable diagram. Let's move on to the next fruit, 9. We scan this max value from 0, we from left to right. 0, nothing is possible. 0, not possible. 5, not possible. We exceeded this. So unset was 0. We were not able to make this as 0. So answer is, in answer, this time it becomes 1. So finally, this is our answer. Okay, let's see the code based on like what we have discussed here, which will and then time complexity and why this is the way, optimized way. Okay, cool. Hmm, cool. I'll remove the code which I've already written. So first thing is we'll take the n, which is our basket start length. Then we have our chunk size. Okay, chunk size is math dot square root of n. Okay, this gives a double and it will have precision issues. So let's convert it to int. And I see on left side also I missed writing the data type. So this is the chunk size. Okay, now number of chunk we discussed, right? Number of chunks will be your total length, which is n, plus add this chunk size minus 1. So if it's a complete length, it won't make any difference. But if it is not, then it will add one additional chunk size chunk to accommodate any extra element divided by chunk size. This is the number of chunks, and this will help us create our max value for each chunk in this array. This will be number of chunks, right? So we got this. Let's initialize this with, let's initialize our array with 0. Now let's take each of the fruit one by one. And we'll try to see, even before passing through fruit, we need to populate our max v array, right? How will you do that is you will parse or scan through each of the element in the basket array, and what you'll do is max of v. For first chunk size element, you'll find the max and put it in the 0th index of max value array. For next chunk size elements, you'll put it in first index of max value array. For next chunk size elements, you'll find the maximum and put it in the second index of max value array. So how will you figure that out is this index correspond to 0th index of max v, first index of max v, or third index of max v is by that index divided by chunk size. So for initial chunk size elements, it will be 0. For next chunk size element, it will be 1. Math dot max of, if the current is the maximum, keep it as is. If not, if basket's ith is more, update this max size with that. That's it. It helps populating our max size array. Okay. Now in the fruits, for each of the fruit, first thing what we have to do is we have to figure out if there is any chunk from left hand side, the first chunk, which can help us accommodate this fruit. So what we'll do is we will say chunk, chunk, yeah, call it, yeah, let's chunk number, which is the chunk number. And we'll also keep an array called as selected. Remember, like in the chunk, if we were able to find the basket, so we were updating that basket and still going through that chunk to update our max v. So for that purpose, this selected will be used so that basket is updated only once, the first basket in that chunk, which is following the rule. So for that, this variable will be used. And also, we will keep our unset as 1. So if we are able to find the basket, we'll make it as 0. If we are not able to find the basket, then unset will be 1 and we'll add it to our answer. So let's have an answer variable, answer equals to 0. So we'll write our certain code here. If we are, let's say, if we are not able to find any basket, then we'll just add unset corresponding to this particular fruit. And finally, we have to return our answer, right? So now whole part is here. Find the chunk and then inside that chunk find that basket, make basket 0, modify your max v, right? So what are the tasks you have to do? Find the leftmost appropriate chunk. After you have find the chunk in the original basket array, in the original basket array, you modify the basket value to 0 so that you cannot use it again, and update your max v, right? Okay, so let us do this part now. For int chunk is 0, chunk, how many chunk would be there? We calculated it for populating this, right? So chunk would be less than equal to number of chunks and then chunk plus plus. If max v of this chunk, if it is less than, your current fruit quantity, then you continue. This is not the leftmost right one, right? Right one. Otherwise, 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 what you do, you make your max v of this chunk as 0 because you need to populate it with new max in that chunk. Okay. And so you need to find the index in the basket array for this particular chunk, right? So how will you do that is int position is, what is the position? It is chunk into the chunk size, right? Now there will be for loop starting from, in let's say I is equals to, starting from position I is less than uh, number of chunks, right? And I plus plus. Cool. So okay, so chunk number or position Uh, chunk we have found. I guess I don't require this. If required, I'll add that. So I have calculated position like this, the starting index of that chunk, and at max it can go till number of chunks. And in the last chunk, if you are there, it might be like if you do number of chunk, it can give you array index out of bound, right? If it's the last chunk, and it doesn't have all the elements, so it won't have number of chunks element. We'll take care of that. So you got the position of the basket, right? So so that it doesn't go out of bound, what we can do is we can take number of chunks or whichever is minimum. Map the mean of number of chunks, n, right? And now, if let's say you find out, you found like okay, this is the basket. How will you do that? Is if baskets of this I is greater than or equal to your fruit quantity, and this is the leftmost. How will you know that? Is if selected is still 0. Because once we find it out in this chunk, we will make selected as 1 so that now you don't go inside this and make baskets of I as 0 so that you cannot use this basket anymore. And you remember max we have modified, so we will have to also this unset was 1, right? So you have found a basket to put it in. So you can make unset as 0. You can make unset 0 here or as soon as you have found a chunk. As soon as you have found a chunk. So if there is a chunk, it means there will be a basket. So you can even make your unset 0 here as well. Let's do that. But anyways, there also it is fine. So let's say if you have found the chunk, then you will make unset as 0. Okay. So if it is true or if it is not true, irrespective of that, you keep, you try to find what would be the next max. But yeah, in this case, let's see if it is 0, so it it might not contribute to your max, but if all of the value in the chunk is 0, then yeah, it will be 0. So math.max of your max v of chunk, sorry. Math.maxv of chunk or baskets of I, right? This is pretty much your code. And the other thing, what one more optimization what we can do is once you have found a chunk, you don't need to look for any further chunk, right? So either you are not able to find the chunk, you kept continuing, or as soon as you found one chunk, you updated that basket and updated the max value. And right after that, you break out of this finding out which chunk to do. You have already placed the fruit. You don't need to further look for more chunk. Okay. This is the code pretty much. Let's try to run and see if there are any typing mistakes, compilation errors. Okay. There are. What is the error? Error bad initializer for loop. Okay, I have not written int. Hmm. Let's try to run again and see. Okay, I have not written int again. Is there any other errors? Let me see. Accepted. Let's try to submit it. Okay, wrong answer. Let me see. What is the issue? Okay, so issue is it won't be like number of chunks, but it will be starting from position. You can go till whatever is the chunk size. Okay, in this. Okay, so sample test case is passed. Okay, so submission is also done and it is successful one. So next, let us look at the time complexity of this. So you see, like for each fruit, we are going through all of these, and for each fruit, first thing is we are trying to find out the chunk. Number of chunk is square root of n. So this traversal is square root of n. Now it can happen like you are not able to find any of the chunk. If you are not able to find any of the chunk, you won't go inside this loop at all. Okay. And let's say if you find a chunk, so it will be the leftmost one. Okay. So if you find a chunk, in that case, you will go inside this only once. Only once. So per fruit, you can go inside this only once. Okay. So, and once you have gone inside this, you can update the basket, and for that particular max v index, you update the max v, and then you will break out of it. Once you have found the chunk, you will not proceed ahead to look for another chunk because you have to look at the leftmost suitable chunk. So if you just look at these, so this is you are parsing through square root of n, and if you found one, then you will look for square root of an element again in that. So it won't be square root of n into square root of n. It will happen when for each chunk you are going through all the chunk size, right? But here you are not doing like that. Like not for each chunk you are going through each of the chunk size. You are first trying to find out the correct chunk. Once you have found out that chunk, which has taken square root of n time, then for that particular chunk you are going through again square root of n. So this is square root of n plus square root of n, not into. So this thing you need to get properly. Like not for each chunk you are going through again all the chunk size. You are trying to find one chunk, the correct one, which will take you square root of n time. Once you have found that, then only square root of n elements you are seeing. So first is square root of n, then square root of n you are going through. So this is square root of n plus square root of n. So that is time complexity is n your n into square root of n. Okay, because this is this total number of time it can go is square root of n, and if you found the correct one, then you will do an extra of square root of n for each n. Right. Hope this is making sense. If not, you can comment in the comment section, and I'll get back to you with your doubts. But I hope this is clear. So square root of n is 1 by 2. So n into n raised to power 1 by 2 turns out to be n raised to power 3 by 2. Or n in this case is 10 to the power 5 into 3 by 2 is 10 to the power 15 by 2, which is 10 raised to the power 7.5, which is less than 10 to the power 8, so it will run. Although it's taking a lot of time, but yeah, this will run. And space complexity is we are taking this max V array of number of chunks side, and number of chunks is calculated based is proportional to this square root of n, right? So your space complexity is big of square root of n. Next, let us try to see why square root of n will give us optimized solution, why not cube root or 1 by 4th root or 1 by 5th root, right? Let me move on to the board. Okay, so we see now, like if you're doing a square root of n decomposition, so the chunk size is square root of n, right? And how many number of chunks will be there of this size? You can evaluate by number of chunks divided total length divided by chunk size, which turns out to be root n. So time per fruit would be we go of root n to find the right chunk. Once you have found the right chunk, then inside that right chunk, you need to again find the right basket, right? So in this case, the time complexity will turn out to be we go of root n, right? Now, what if we try to do a cube root decomposition? So our chunk size will be n1 by 3. The number of chunks will be n divided by n cube root, which is n2 by 3. So time per fruit will be first you'll have to find the right chunk, which will be n raised to power 2 by 3. And then to find the right basket within that chunk, you'll have to go through that chunk size, right? So n by 3. So I mean, which one dominates over these two is this, right? So this becomes n by 2, n raised to power 2 by 3. And if you see n raised to power 2 by 3, it increases your time limit. And if you do this, then it might break. So in general, if you let's say if you take a 1 by kth power of n, the size of chunk size, in that case, chunk size n raised to power 1 by k, and number of chunks would be this, right? Now per fruit time would be your n raised to power k minus 1 by k to find the right chunk. And after you have found the right chunk, then inside that you have to parse with these many elements to find the right basket. Okay. So so in general what happens? So your time limit will depend on max of n raised to power k minus 1 by k n raised to power 1 by k. If you see if your k is 2, what it becomes is n raised to power, so n raised to power 1 by 2. If your k is 3, it becomes n raised to power 2 by 3, comma, raised to power 1 by 3, raised to power 3 by 3. If your k is 4, what it becomes is n raised to power 3 by 4, n raised to power 1 by 3. So similarly, if you go down, you will see like your time limit keeps increasing. So this is I have shown you with the value. To get the exact value to, what you need to do is this is your max. I mean your time complexity depends on these two, right? And actually in summation of these two, n raised to power k minus 1 by k plus n raised to power 1 by k. So the best way to come at value what k will be 2 is you need to do differentiation, right? And if you do double differentiation, you will get exact value like okay 2 is the value wherein this equation will give you the uh, least least time complexity. Okay. Yeah, if you want me to do a differentiation for this, I mean initially see I can help you like what needs to be done here for doing a differentiation of this. So you can convert it into logarithm terms since powers are there, so that will help you. And if you want me to do a derivative of this and show you like even after doing single derivative, you can find your local minima and do it. Or if you do it double derivative, it will be the best one. Like you can be sure like okay, this is the global minimum. After that, you are not going to find a minimum. So yeah, that way we can conclude. But yeah, do let me know if you want me to do a differentiation of this and show you like 2 is the value where this function will have the minimum value. So yep. That's it for today. I hope I made sense and gave you knowledge. Let me know if anything I need to improve on. Thank you.